Linearization, it's I always say it falls under the category of cool math, and cool is relative, right? Because I know that the way I use the term cool is maybe not the way you all do, and I don't even know if you use that word anymore. Uh, it's now an old person word, I guess. No, it's fine. It's just it's not when I say something's cool math, it's basically saying that it's of the theoretical variety. It's got some nice attributes to it that's like, oh, that's interesting, but I like on an everyday life, no, you're not going to use it, but it advances the cause. It's another way of applying some of the things that we've already learned. I look at it as a segue to the physical applications to the calculus that we've covered. All right, so it's kind of a stepping stone. All right, so one of the things, and because people always ask the question, why would I use this technique to find a cube root of a number when I could take out my calculator and type in the cube root and get the answer that way? 15 years ago, 20 years ago, I could say, well, you might not always have a calculator. Well, nowadays everybody's always going to have a calculator. It's just the way it is. I mean, even if you don't think you have a calculator, you have a calculator. All right. So your phone has one. You already knew that, but I found out the other day that my car has one.
What?
Even without, yeah.
May I ask what kind of car you have?
It's a Honda Civic.
And it has a calculator?
Yeah.
How so?
It's in the dashboard settings. In the
My car is a simpleton.
the CarPlay interface, and I'm talking like without the phone even being plugged in. So it's not running off the phone.
Is it like a graphic?
It's a scientific calculator.
Guys, I can't
Yeah.
hear that.
I did not.
Don't drive.
and drive.
Oh boy.
Come on, that was good.
Am I having a big clapper in
Very
this,
nice.
in this class? I want to make a big clap.
That got turned around on me very quickly. All right. Anyway, so yeah, you're not going to be using this concept in your everyday life, I don't think. But this concept is used in your everyday life, whether you choose to believe it or not. Computing software, when it actually determines things like cube roots, square roots, and stuff like that, it's actually using a variation of this approach. Right? When you search for online, like the derivative, you find some Symbol Lab or something like that, some app that does the calculus for you. It's not actually applying the power rule. It's doing this stuff behind the scenes and then coming up with a numerical analog to whatever the actual function is. All right, and so even something as simple as your math 8, when you do y4 in your calculator, all this stuff is happening behind the scenes. Right, so I thought it was worth spending a little bit of time trying to understand where it came from, why it works the way it does, with the expectation of, like, I always think about it like, can you use a hammer? Sure. Do you need to know how a hammer is built in order to use that hammer? No. But if you turn the TV on and you see that somebody has there's a documentary on how hammers are constructed, depending on like what your interests are, you may find yourself, oh yeah, that's kind of interesting. Like, I didn't know that's how they forged the hammerhead. Like, oh, birchwood tree, I didn't know that. Like, so, like, these are some things like you might find it to be interesting, and so that's what I categorize this as. All right, so, and I'm only getting into this, like, before it was like derivatives. Why are we learning about it? Because this is a class called calculus. And you have to, and it's important, and it's rates of change and stuff. The selling point on that was, well, you took the course to learn about derivatives. This I feel like I really have to sell, because when we get into it, you're going to be like, whoa, there's no valid reason why I need to learn this. But if you have in mind that it's just kind of learning a different aspect of calculus, a little cool math application, then I think that'll serve you well. So number one, determine the linear approximation model. So very, very important, folks. Linear approximation. By the way, we're big on synonyms in this course. Like, everything meant derivative in the first semester, right? It's like, what's the question that they're asking you? Slope of the tangent line, instantaneous rate of change, blah blah blah, whatever it was. It was saying find the derivative, all right? So we have synonyms here too. Linear approximation model, tangent line. So then you look at that moderately intimidating formula, the L of x equals f of a plus f prime of a times x minus a. But then you compare it to the point slope form of a linear function, and really you see it's exactly the same. All right, structurally, you have y1 in the place of f of a, you have m in the place of f prime of a, but more so intuitively, and by definition, they're the same because m is slope, and so is f prime, slope of the tangent line. So m is a more universal representation of slope, but in this context, it just means slope of the tangent line. All right, so determine the tangent line model for this function at x equals 8. All right, we've done that a bunch of times. So I have my f of x. I'm going to write it as x to the 1/3 power. Now, something very, very important that some of us are going to miss. We want to be able to do this without using the graphing features on our graphing calculator, right? Because it kind of defeats the purpose. Because I don't want you to say, well, I could just use the function, or I could just use y4 to do it. Like, I want you to kind of limit yourself to the 4 functions on your calculator, right? In order to do this, all right? Now, I'm not gonna restrict you. You can use your calculator. I mean, I do have a set of 4 function calculators, but I think that might be going a little overboard. But yeah, restrict yourself to just addition, subtraction, multiplication, division. All right, and try to do as much of it as you can in your head. All right, your head. I don't know why I said it like that. Do it in your head. Upside the head. So the derivative of the original function, 1/3 x to the negative 2/3. We're doing this all when x is equal to 8. So f of 8 and f prime of 8. And the problems I chose them because they're clean. So you do have a fighting chance to do these in your head, even the trig functions and the exponential functions. All right. So 8 to the 1/3 power, also known as the cube root of 8. 2.
Hey! That's it.
You sure did. You sure did.
Participation.
Yeah. Getting it done. Now you may look at this expression and say, yeah, I don't know about this.
So now we started writing this?
No, you still do it in your head or by hand.
Boy, they.
But what I suggest is that you dial it down before you dial it up, because when you're dealing with a fractional exponent, I always work bottom to top. Denominator, numerator, positive or negative sign. All right, so denominator is the root. So what's the cube root of 8? 2. The numerator is the power. So what is 2 to the second power? 4. The negative sign tells me to take the reciprocal of that. So the reciprocal of 4. 1/4. So I have the 1/3 out in front. Multiply it by 1/4, you get 1/12. All right. And so what I want from this is the linearization model. So L of x instead of y is equal to f of a, which is 2 instead of the y1, plus f prime of a times x minus the given a. All right, that a value is the 8 that they gave us. All right, and so what that model will do is it'll give us the linearization for any particular value. But more particularly, we want to think of it as an approximation. All right, so you're thinking, all right, I can use this formula to help me approximate the value of the cube root of 8.05. Because the trade-off is, let me pause. All right. So, I mean, honestly, if I gave you a choice, just without looking at any of this work, if I say you could have a really complicated curve function to work with algebraically, or I can give you the equation of a line, that it'll have some inaccuracy, but it's going to be close enough to the result for that curved line that you could use that instead of whatever you get when you plug into the curved line. Like, which are you going to choose? The really complicated curve or the simple line? The simple line. All right. So we have a curve. I wouldn't categorize this as complicated, but it's a curve. I mean, if you look on the next page, you'll see complicated. But this is a line. By definition, a line is never going to be as complicated as a curve. All right. So when I want to evaluate 8.05, all I have to do is pop that into this function. So L of 8.05. So we're looking at 2 plus 1/12 times 8.05 minus 8. And again, it becomes more and more surprising that these are things that you could do in your head. But this is also, even though there's a decimal there, this is also something that you could do in your head. So order of operations, what's 8.05 minus 8?
0.05.
0.05. What's that in fraction form? 1 over 20. All right. What's 1 over 20 plus times 1/12? 1 over 240. So we're looking at 2 plus 1 over 240. Because remember, when you're multiplying fractions, just top by top, bottom by bottom. So 1 over 20 times 1 over 12, it's going to be 1 over the 12 times the 20. All right, so to multiply 12 by 20, you just multiply 12 by 2, just tack a 0 on at the end. All right. Honestly, it sounds weird to think about this, but, well, maybe it's just weird on my end. I really actually enjoy talking about like mental math strategies. Like I have the same conversation with my son, who's in 4th grade, that I'm having with you now. Like, how could you multiply this by that? What are you thinking? What should you be thinking? What's a better way to think about it? Because honestly, mental math is something that you can all get. You just got to work at it. And you know how I got good at mental math? It's the dumbest thing ever. Or at least I think it is. Unless you all tell me it's really cool, in which case I'll revise my opinion.
Counting ducks.
Not too far off.
Counting money.
Nah.
You wanted to go to the ball game.
It was nothing practical.
Okay. Lego building, strategic. Anyone else have any guesses?
It was nothing organized. I didn't go to a camp.
Okay.
Nobody, I didn't do a program.
You calculated.
There's no Rosetta Stone.
Something about, can you give us a hint?
It happened in the car.
Songs. You were distance and time. Maps. No.
Distance and time. Miles per hour, but specifically, so I'm traveling, so I know that I can get to a certain place in like an hour if I travel at 60 miles an hour. So I just started screwing around and I would say, okay, well, what if I go 80 miles an hour? And so I just start running the numbers. Now, it's not complicated math. You know what the distance is. You know what the speed is. You just have to do the actual multiplication division. Yeah, but... Well, that wasn't the intent of the example, but you get the idea.
You taught us an important lesson. Yeah. Go faster and get there quicker. All right.
So, shockingly, the lesson that is in what I'm sharing here is that I did the math, and I'm like, whoa, I'm only going to get there a minute and a half faster? Or it was a little bit bigger, but not appreciably bigger.
Oh, so we shouldn't speed. All right.
Yeah, but... what I was doing was I was trying to figure out all this stuff. The radio is on, or I was listening. I had a YouTube channel on, or whatever. I was like, okay, you're distracting me. Mute. So I could concentrate. So like the time, like you want to carve out some time to practice mental math, you can do it by sitting at a desk in the library and expect quiet concentration. Or you could just take one of those moments where you're alone and you have nothing else going on and just make it about that for a couple of minutes. It goes a long way. Right? So it's kind of weird to think about that, but it is something. That's how I got good at it. Like like that kind of stuff comes naturally to me now because on my off time, church, during church,
Can't relate.
yeah, I like a graduation ceremony. Yeah, like
Yeah, that's facts.
a study hall if you're a freshman. The end of a test where you can't use your phone. Like I've had students that like, how many people know like a significant number of digits of pi from an experience in the middle school?
From watching the movie Pi.
3.141592653. That's all I know.
Is it because of the wall?
159265335.
Yeah, because you had nothing better to do, so you're like, all right.
4 after 6535.
Honestly, I have no idea. I've never been that poor. So.
I think it's 26535.
My dad, when I was younger, I would like ask him to go to the turf with me so I could like practice, and my parents would be like, well, you need to practice your math thing. So like he would only like roll me a ball if I like answered the math question. But then I just stopped practicing with him.
Your dad like an English teacher?
Yeah, my dad's an English. Yeah, but like it was like mental math. He was asking me. He would be like
5 times 8.
couldn't tell you. 40, I guess.
40.
Is that even it?
It
Yeah. The kid I babysit, I have to help him with his homework, and like he'll do stuff. And
Welsh knows everything.
I like get it in a second. He takes him so long. I'm like, you really don't know, like. 5 times
Grow up,
8.
kid. Get it together.
You're 5, so I'm 5.
I don't say that. I'm just like, you know that. You know, the problem with math tonight. Really? Their math, elementary school math is so weird. It's so weird. They make them do the weirdest things. It's weird.
Some of it's really good, but some of it I'm like, ooh.
Break it down so much and make them do horrible boxes and so annoying to teach about.
You know what it is? It's because they're trying to manufacture intuition. And that's just so hard to do because the person who created the lessons, they're trying to teach their own brand of intuition. And we all know, like, what's good for one person is not going to be good for another. Like, my son was studying for a social studies test for today. My wife, she knows how she prepares for tests. So what she did was she created a summary of his entire chapter. 30 pages down to 10. And so she hands him 10 pages to study. And he looks at it and says, the hell is this? Like, I gotta read all this? She's like, well, it's either that or the 30 pages in the textbook. And he's like, but I already read the 30 pages in the textbook. Why do I have to read this too? And so she has her own way of thinking that would get the job done that he can't relate to in any way. So the fireworks flew. That was a battle royale. But I enjoyed the show.
Learn it from just reading it. Like, yeah, I guess if I underline it, but I like write things down. Like I rewrite
Yeah.
everything because then it's like.
That's how I learn by reading.
So like I'll rewrite all my words with the definitions and then. That's
Right, but like highlighting the key points.
Yeah.
Right. That's how I do it too.
Much though is writing it down.
Yeah.
No, I read it and then I'll think of like when I'm in the test, I'm like, oh, it was on that place in the page.
Oh yeah,
And I can
yeah.
like read it in my
Colors.
head.
Oh, yeah, photographic memory.
It's not really photographic. It's
It's just like where was it placed on like the if you have the study guide.
Yeah.
If they give you study guide, you're like
It was
on the
there.
second page in the middle of the page. Like
And I
something
can
like
see it.
that.
Yeah.
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 It's not really, but I think it's more.
Well, because there's a difference between photographic and eidetic memory. Photographic is you could see the image in your mind of the thing that you're remembering. Eidetic is where you could actually remember everything that was on the page also. So, like, if you're seeing in images, like, if tomorrow you think back to this lesson and you could actually see, like, even one line of what I wrote there, then that's photographic. You know, it's just not eidetic, you know? So...
I like how you write in colors too. That's why I always write everything in colors.
Yeah, I try to alternate because like I need it to pop, you know.
No, it works. It's like a lot easier to remember.
So then, all right. Well, after all of this, I would imagine we'd want to have a sense of whether or not we did any of this right, right? So
now we plug it, throw it
now we go to the calculator. So math, option 4, pop in your 8.05. So I get that number. I almost said name. So then I need 2 plus 1 over 240. Folks, mixed numbers are the way to go in this topic, just because it makes it overly complicated if you go in terms of improper fractions. And also, it's a good way to kind of handle it, to think, well, my calculator says the cube root of 8.05 is supposed to be 2 and change. I got 2, and that looks like the and change part of it, right? And maybe you don't even need the calculator, because if you know that the cube root of 8 is 2, and 8.05 is a smidge more than 8, then you expect your answer to be a smidge more than 2. So we just did all this work. 2 and 1 over 240 is a smidge more than 2. So it feels right. All right. Now, this is the key to everything. 8.05 was good with this model, but 25 is not going to be good with this model because, as you can see in the diagram, we have a curve and we have a tangent to that curve. As you move along that tangent, your level of accuracy decreases. All right. So if you're right at that point of tangency, the curve and the line have the same value. But as you move further along that tangent, the whole going off on a tangent thing, which is kind of the name of the game here, like that's where it's from. So if I try to use this model with a 25, I'm not going to get anything near the right answer. So what I'd want to do is reevaluate and determine what an appropriate A value ought to be for 25. All right? So let's kind of partition this off. And actually, let me make that smaller. All right, we're working with a cube root function. If I want to evaluate 25, I want to find the cube root of 25. 8 was a perfect cube, right? Yeah. So that made the numbers nice to work with. So give me a perfect cube that's near 25. Well, 16 isn't the perfect cube. 27, yeah. If you're looking for perfect fourths or perfect squares, 16 would do the job. So 27, we know what our derivatives are. We know what our value is and we know what our derivative is. So we're going to evaluate those for 27 now. So because it's a nice perfect cube that's near the number that they're asking us about. So f of 27, f prime of 27. So we're going to come up with a new linearized model for this particular A value. All right, so 27 to the 1/3, and then 1/3, because I'm just popping it into the derivative, times 27 to the negative 2/3. All right, 27 to the 1/3 is? 3. That was the reason why we chose it, because it was a perfect cube. Now, again, bottom to top in your fractional exponent. The cube root of 27 is 3. Squared? 9. Take the reciprocal. 1/9. Take that 1/9, multiply it by the 1/3. 1 over 27. So I have L of x is going to be equal to 3 plus 1 over 27 times x minus 27. Now it's coincidental that my slope and my x value both involve a 27. That's not always going to be the case. Sometimes it happens that they're reciprocals, but not always. All right, so now I'm going to evaluate this for 25. All right, so this is really asking us to determine what 3, because 25 minus 27 is negative 2, multiplied by the 127 is going to be negative 2 over 27. All right, so I just need to take 3 and subtract from it 2 over 27. All right, so I know it's going to be 2 and something. So, say it again. Yep. So really all you're doing is you're just stealing 1 away from the 3 and making that a 27 over 27 and then pulling 2 out of 27 from that. All right. Now, is that right? Is it wrong? Well, the cube root of 25, and I'm not even going to pop this into the calculator because I know it's going to be pretty close at a minimum. The cube root of 25 is somewhat lower than the cube root of 27. Cube root of 27 is 3, so I would expect the cube root of 25 to be somewhat lower than 3. All right, so that's what we're getting. Some value that's somewhat lower than the 3. All right. Now, the last one I wanted to go over is the trig problem. Very spicy looking problem. It's actually the easiest one. You know, because that's the thing. Hopefully, you know, like at least for the simpler trig functions, you've come to realize that trig is not something to be intimidated by anymore. You know, because numerically the numbers end up being pretty all right. There really isn't much that you have to do with the derivative. I mean, anything's going to be more complicated if there's product, quotient, or chain rule or anything along those lines. But just the act of finding the derivative of a trig function is usually easier than doing the same thing but with a root function. All right, so let's take a look at f of theta is equal to the sine of theta. All right, so what's f prime of theta? As in the derivative of sine. Cosine. F of 0 would be the sine of 0, which is 0. Now, I know a long time ago I promised you that we would be doing some unit circle quizzes, and I kind of put them on the burner. And then we did that bonus assignment, so it seemed like it was on the horizon. We're going to start doing those pretty soon. My intent is to give you 5 of them, right? So, but they're like, we'll go over how to construct the unit circle again, but I just wanted to let you know that that's going to be a thing. And that's a thing to look forward to, because once I show you like what you'll be doing, then you'll have the quiz. You'll know it's going to be on it. You just got to do it. Cosine of 0, 1. All right, because these numbers should be kind of rattling right off your brain. So L of x. Oh, I'm sorry, L of theta. They changed the variables on me. Would be equal to 0, 1.
I'm stuck in the corner.
Ah, poor guy. At least it's not a situation where it's necessary to open a window. Because if you're stuck in the corner under those circumstances.
I'll be done. Thank God those were
All right, so we get L of theta is equal to theta. You're pinned in the corner.
You turn your cheek and things cheek. That's a good one. Take that one.
I didn't hear it.
All right, so we get L of theta is equal to theta, which is really the same idea as y equals x. So this is kind of a nice consequence, because really if you think about it, what we're able to do now is for values close to 0, we're able to approximate a trig function with a simple linear equation. And you'll find, like the further you go in calculus, and I'm understanding the realistic nature of this, but, so like some of you may not go further in calculus, but if you do, you'll see that there's more and more topics that involve taking linear equations and polynomials and using them to model the more complicated ones. Because again, it goes back to the idea, do you want to work with something easier or you want to work with something more challenging? All right, so we have the sine of x and then y equals x. You graph it, I'll just bring it in because I can. I think, honestly, I don't think this is an inappropriate use of the word obviously. So obviously, on this interval, just for this little piece here, I think it's pretty easy to see that the line and the curve are virtually indistinguishable from one another. So that's basically saying that I can use that line y equals x to approximate the sine function. And I joked about this with the period 3 class, and I said, if the only thing that you get out of this is that when you're sitting in a calculus class next year, if the professor says, all right, somebody tell me what the sine of pi over 12 is, and then you reply back, it's pi over 12. The teacher may say that you're wrong, and then you reply, well, I was just using the linear approximation, and that just tells us that x and y are approximately the same. So I was just giving you the approximate value. They may just give you the A right there. Like that might be the end of it, because that's like, whoa. Like I'm dealing with some big time student here. So, like there might be something there. All right, so.